Hello, and welcome to the official start of this ICSE session on software testing 11. We've got a great lineup in this session of 6 presentations, papers. It's a blended session, as with the rest of the sessions across the various tracks at ICSE, all on the topic of testing. As a reminder of the format of this session, we have these 6 presentations. Each presentation will be 5 minutes. We'll go straight back to back with those different presentations. And then at the end of all of those presentations, we'll have a large open Q&A discussion where we'll invite everyone to ask questions. As the speakers are presenting, you can feel free if you have questions that you just really want to make sure to get out there. We would love for you to share them in the chat. To share them in the chat, you can click on the question button directly above the chat entry box, which will format your message as a question, make it easier to see. I'd also encourage everyone who's watching, and perhaps even the authors, as we get through the presentations, you can use the emoji reacts under the chat box to send reactions like applause, for example, while the presentations are going. It's a nice little way to remind everyone that we're here and mention, our reactions. So with these matters out of the way, I'm happy to introduce our first presenter. It's going to be Stefan. Will be presenting smoke testing for machine learning, simple tests to discover severe defects. And Stefan, the floor is yours.
Yes, thank you for the introduction. So this is joint work with Tobias Haar, who did most of his master thesis in this direction. And what we were interested in was not testing of machine learning in the sense of let's test our model, but rather let's test the libraries we're using. So let's test scikit-learn, let's test Apache Spark, let's test Weka or similar libraries. And moreover, since a lot of research in recent year was tailored towards deep learning libraries, we looked more at the general purpose libraries with decision tree, logistic regression stuff. And what we did was we wanted to look at smoke testing. And this is defined by the ISTQB as a test suite that covers the main functionality of a component or system to determine whether it works properly before planned testing begins. And we just interpreted this as the crucial functions shouldn't crash before you start your main test campaign. So we thought about what are the crucial functions here? Well, the main machine learning workflow more or less looks like this. We have training data, we feed it on our learning algorithm, we get a model, we then feed in more data for testing, and we evaluate it. So this is what should be working. We must be able to train with our data, and we must be able to predict with our data. And this shouldn't crash. So we have a very simple test oracle. If the libraries crash, it's probably a bug. And we wanted to use basic techniques for that. And one of the most basic black box testing techniques are equivalence classes. So you partition your input space and you say, this is valid, this is invalid. Unfortunately, with machine learning, valid basically means all numeric data, all categorical data, and often all combinations of both. So more or less, any data you can think of is usually valid. So that didn't really work out. And ideally, when you have equivalence classes, you can do something like boundary value analysis to find good candidates for testing, where you actually look at the boundaries between this. Well, if we have this huge space of equivalence classes, the boundaries are basically just the machine precision. So again, not a good source for many test cases. So we went back to the drawing board and considered what's problematic for machine learning. And there are many corner cases, and these corner cases are basically based on the probability distributions as input. So often you hear something about normality assumptions or well-behaved data, skewed data, and so on. And we thought, well, maybe algorithms actually have problems with that. So we thought about these equivalence classes. And the simplest one is you just take uniform data in the interval 0, 1. That's the most well-behaved data you can more or less have, and it's working. And then we went ahead and thought, what are difficult cases? And well, of course, we take the machine precision. So what happens if we go to the maximal 64-bit numbers or 32-bit numbers? What happens when we go to the smallest numbers? So between 0 and 10 to the power of minus 14. That's what double can provide us. And what happens if we actually input only zeros? Or if we have very skewed data? Or one single very, very large outlier? Or if our test data is in a completely different range than our training data? And so on and so on. So based on this, we defined 22 smoke tests. All of them can be implemented in really 1, 2, 3, 4 lines to generate the data. And we then ran 19 clustering algorithms and 53 classification algorithms of scikit-learn, Weka, and Apache Spark here. And those are basically all clustering and classification algorithms that these packages implement without any plugins. And we found some pretty bad bugs, even though our approach was pretty simple. So especially looking close to machine precision with very large values was efficient. We had stack overflows and out-of-memory errors in Weka due to a bad recursion. We had memory errors in scikit-learn with 5 input values. We had illegal number of clusters with Weka. We had test cases that were also pretty simple. So only put in zeros and you could crash the nearest centroid classifier. Use only a single class naive Bayes crash, and so on and so on. And obviously we wanted to have this fixed. So we wrote up the issues, sent them to the developers, and the reactions were actually interesting and different for each framework. Scikit-learn, it's mostly fixed or a work in progress. Weka, yes, those are bugs. We would merge them, but we're in such a deep maintenance mode, we won't do it ourselves. Apache Spark, okay, yeah, that's a bug, but such a corner case, we don't care. So in the end, the key message is, do not forget the simple tests. So yes, we need complex test campaigns for this sort of software, but with simple tests, we can already find bugs. So use a smoke test suite. And don't forget the hyperparameters. I mean, I have limited time here, so I didn't talk about that, but there were tests we only found because we swept the hyperparameter space as well. Okay, then thank you. We were also on a podcast with this paper if you want to listen to that. Yeah, I'm looking forward to the discussion later and the other presentations.
Thank you very much, Stefan. Very, very nice 5-minute overview of what sounds like an extremely interesting and large study. The next paper that we have scheduled was algorithmic profiling for real-world complexity problems, but I haven't heard from any of those authors, and I don't see any of them here. So maybe I'll just wait like 2 seconds to make sure that nobody speaks up in the chat. And then we'll move on to the third paper in this session, build system-aware multi-language regression test selection in continuous integration. And Daniel will be presenting that. So go ahead and take it away, Daniel. Thank you.
All right. Thank you very much. So this is joint work with our industry partner, IFAU Traffic Technologies. And we actually applied and deployed the system that we developed in this work in their CI infrastructure since September. So I'm just going to give a brief summary of the work since we have limited time here. And I want to give a bit of background on the context at IFAU. So IFAU maintains several release branches of their main software. And whenever there's a change that someone wants to make on these release branches, the developer has to create a pull request. And for that pull request, a CI pipeline is then triggered and run. So the code is built, analyzed, and tested. And as you can already see here in the small illustration on the right side, the code base is split into 2 parts. There's a C++ subtree and there's a Java subtree. And whenever you make changes to one of the subtrees, certain steps get triggered and other steps won't. And if you have, for example, a change to the C++ subtree, there's a specific, it's specifically interesting because in this case, also the Java code base has to be built and tested. And this is due to a lot of cross-language links that are prevalent in the software. So they use the Java native interface to have some cross-language links implemented. So Java code, Java tests will actually use some dynamically linked libraries, C++ code, also throughout their execution. And the problem with these CI pipelines is that they take a long time to run. So building the code base takes a long time, and testing as well. And we wanted to reduce the effort specifically for those Java parts of these pipelines. And the problem with existing safe RTS, so regression test selection techniques, is that they're impractical in this case because they largely rely on a compiled code base being readily available. So they use checksums and that class files in the Java case. And for this, we would have to compile the code first before we can actually run the selection. And the second problem is that they're not built for multi-language code bases. And as I said, we have a lot of cross-language links in this case. And those are not only limited to the Java, C++ interoperability, but also related to domain-specific languages such as XML or SQL. And the proposed solution in our work is that we build a technique that's build system aware. And so we only have selective build. We only build those modules that are relevant for the changes introduced in the pull request. And also it's multi-language aware. And we implemented that using language agnostic system call tracing. So we know for each test, what are the files that are being opened throughout the execution of the test. And what came out of this is here displayed on the right side. So we were able to actually reduce the effort for building and testing the software. And our results that we obtained in a 5-week case study at IFAU is that we find we can reduce the testing duration actually by 42 to 72%. It depends on the how old the release branch is that we evaluate this on. And we find no real missed failures. So we find some flaky failures that are missed by the test selection. But there is several sources of unsafety here. For example, the test traces that we collect every day, and then they're used for the next day, could be outdated. And also detecting some dynamic changes in the code, for example, through dependency injection, that's also something that is not yet accounted. And we're building upon this foundation that we've built in this work and trying to improve it. And for the end-to-end pipeline time reduction, we find that we can actually reduce the time here for these Java steps by 50 to 63%. And as I said, it's now deployed at IFAU in all their release branches since September. And that concludes my presentation. Thank you.
Thank you very much, Daniel. Very interesting study. Always interesting to see these techniques being applied at scale in the real world scenarios that developers are actually using. Very cool. Look forward to discussing more about this. But let's keep things moving along. The next presentation in the section is going to be given by Anjiang on free lunch for testing, fuzzing deep learning libraries from open source.
Hi everyone, I am Anjiang Wei, and I'm going to present my work on free lunch for testing, fuzzing deep learning libraries from open source. This is joint work done by me and my collaborators, Yinling, Chen Yuan, and Ling Ming. We're from Stanford, Illinois, and Nanjing University. Let me start by showing you one example bug found by our tool called FreeFuzz. This bug is an interesting one because for the same test input, the API torch.nn.maxoutput2d throws an exception on CPU, but passes silently on GPU. After careful inspection, we find that the exception is actually expected because the input is actually invalid. So GPU produces a round result silently on PyTorch without throwing any error. FreeFuzz finds these bugs because it applies random test input generation and differential testing. Now you may be wondering this question: how does FreeFuzz know the right types of parameters for invoking these APIs? For example, this maxoutput2d API. So this is the challenge of our work on fuzzing APIs, because APIs in deep learning frameworks are mainly exposed in Python, a dynamically typed language. Therefore, it is hard to determine the parameter types for test input generation. Let's take a look at the conv2d's API definition in PyTorch official documentation. Based on the API definition itself, we can hardly infer the type information. Luckily for this widely used API, the documentation provides some information about type. Instead of mining from this natural language description, the way we resolve this challenge is by dynamically tracing the API invocation when running existing code. We record the parameter types and values in the instrumentation, which will guide the fuzzing stage later. Next, I will gradually show the overview of FreeFuzz. The first stage is code collection. As shown in the figure, FreeFuzz obtains code from 3 different sources. The first is code snippets from library documentation. The second is library developer tests. The third is various DL models in the wild, all of which can be obtained from open source automatically. The second stage is dynamic tracing with instrumentation. FreeFuzz first hooks the invocation of APIs, then executes the code collected in the first stage to trace the dynamic execution information for each API. As a result of this second stage, FreeFuzz will construct type space, API value space, and argument value space for the later fuzzing stage. The third stage is mutation-based fuzzing. Basically, FreeFuzz effectively generates mutants for the test input used to invoke the targeted APIs, based on the traced information collected in the second stage. The mutation strategies are composed of type mutation, random value mutation, and database value mutation. Last stage is running all the generated tests with oracles. FreeFuzz resolved the test oracle problem by differential testing and metamorphic testing on different backends and hardware. FreeFuzz is able to detect various types of bugs, including wrong computation bugs, crash bugs, and even performance bugs. In conclusion, in this work, we propose FreeFuzz, the first general purpose and fully automated API-level fuzzing for deep learning libraries. The reason why we call it a free lunch for testing is because FreeFuzz mines code snippets from library documentation, developer tests, and DL models in the wild, which all of which can be obtained from open source. After that, FreeFuzz mutates the traced input via type mutation and value mutation. It can detect various bugs via differential testing and metamorphic testing. It's worth noting that our idea of fuzzing from mining is actually generalizable to other domains. So far, FreeFuzz has detected 49 bugs for PyTorch and TensorFlow, with 38 of them confirmed by developers as previously unknown. FreeFuzz can also cover 9 times more APIs than prior work with only 3.5 times lower overhead. Our code is publicly available. Thanks for your attention.
Thank you very much, Anjiang. Another very interesting paper applying testing techniques and finding real bugs. Very exciting. The next paper that we have in our session is going to be presented by Xin Yu on automatic detection of performance bugs in database systems using equivalent queries. Go ahead, Xin Yu.
Thanks for the introduction. My name is Xin Yu, and I'm presenting automatic detection of performance bugs in database systems using equivalent queries. This is a joint work with Qizhou, who now works at Meta, Joy Aruraj, and Alessandro Orso, who are my advisors. The motivation behind our work is that it is important to have suitable testing techniques for DBMS correctness and performance. However, most recent research only focuses on DBMS correctness. The same scrutiny has now been applied to DBMS performance. Performance bugs are misoptimizations in DBMS that cause delayed response time. For example, assume we send this query Q1 to the DBMS, and it costs us 13 seconds. But looking at Q1, we notice that the limit keyword only asks the DBMS to give us the first satisfying row. So the query should have executed much faster. The delay is in fact caused by a performance bug that makes the DBMS ignore the limit keyword. In general, performance bugs can cause significant delay on response time from the DBMS, which can dramatically affect the user experience. However, detecting such a performance bug is very challenging because there's no general way to define the expected query completion time for a query. To address this challenge, we propose Amoeba an approach based on differential testing. We construct semantically equivalent query pairs and run each pair on the same DBMS and compare their execution time. If the time difference is significant, that indicates a potential performance bug. Amoeba has three main components: generator, mutator, and validator. The generator is responsible for generating queries from scratch. Those generated queries later will be used as seed queries for query mutations. The mutator is responsible for mutating base queries while preserving their semantics. The validator will run equivalent queries on the same DBMS and reports a performance bug if the time difference is above a given threshold. The generated bug report includes equivalent queries and their corresponding execution plans. In addition, Amoeba is also equipped with a feedback mechanism that allows it to focus on exploring a subset of query space that is more likely to discover potential performance bugs. In our evaluation, we applied Amoeba on two DBMS, CockroachDB and PostgreSQL, and investigate a number of research questions. In this short talk, I will focus on the evaluation on the effectiveness of Amoeba in detecting performance bugs. This table summarizes the total number of potential performance bugs Amoeba discovered and the breakdown of those numbers in feedback. The key takeaway from the table is that Amoeba discovered 39 potential performance bugs in two widely used DBMS. Among those bugs, 6 + 1 have been confirmed and fixed. The +1 in parentheses is a bug report that was not officially acknowledged but matched a planned fix. This table also shows that Amoeba generated 1 false positive for each DBMS. In addition, 4 of the PostgreSQL bug reports were classified as missing optimizations instead of bugs. The remaining reports for CockroachDB were backlogged, whereas the PostgreSQL developers asked us to post them together on their wiki page, which we are in the process of doing it now. Overall, we believe this result shows that Amoeba is a useful tool that can automatically report to developers potential performance issues that may need consideration and assist developers in analyzing the root cause of these reported issues. To conclude, performance bugs can cause significant delay in DBMS response and dramatically affect the user experience. Amoeba is able to detect such performance bugs by having a feedback-guided equivalent query generation techniques, which allows Amoeba to leverage equivalent queries as differential performance oracles for finding performance bugs. Our evaluation on 2 DBMS is promising, showing that Amoeba can, at least in some cases, find real performance bugs in widely used DBMS and provide useful information to developers. Thanks.
Thank you very much, Xinyu. Very interesting work. Look forward to talking more about these oracles that I guess continue to plague all of the our testing efforts here. As a matter of just administrativia, I wanted to note the authors for algorithmic profiling for real-world complexity problems are now here. We're just going to continue in order first, though, and finish off with Xuan's R2Z2 detecting rendering regressions in web browsers through differential fuzz testing. And then we'll wrap up coming back to algorithmic profiling. So go ahead, Xuan. Thank you.
Okay. Thank you. I'm Xuan Song from Seoul National University, and this is a joint work Samsung Research and Google. So I present the summary of our paper, R2Z2, which find the regression rendering bug in the browser through differential testing. As you can see from the title, our research is looking for rendering bugs. So first, let me explain what the rendering bug is. A rendering bug is a bug where the web page is incorrectly displayed in the browser, so it can damage the reliability and fidelity of the web page. Here is the example code with its correct and incorrect result. In this example, CSS here, CSS style filter is applied to span element. So the correct rendering is to paint the span element with gray. However, on the bottom figure, the figure incorrectly paints the outside of the span element with the gray as well. This is another example that the real website was damaged by a rendering bug. Originally, the Apple website should look like the figure on the top, but as you can see from the bottom figure, some part of the menu bar disappeared due to a rendering bug. Now you can see that rendering bugs are so critical to the web pages. However, even though the rendering bugs are important, many rendering bugs remain in the browsers. We think this is because, unlike the memory corruption bugs, there is no rendering oracle which can tell the correctness of the result. To be more specific, in the case of memory corruption bugs, we can develop an oracle such as address sanitizer because we can define the valid and invalid memory regions. However, in the case of rendering bugs, it is difficult to design a rendering oracle because it is a semantic bug. So to make a pseudo oracle, many tools simply employ a differential testing approach. They compare the result of two different browsers and determine that there is a rendering bug if the two results are different. This approach has been widely used because it requires little domain knowledge. However, differential testing has a critical limitation. It can generate many false positives because of benign browser incompatibilities. In short, the results are meant to be different. We found that there are two prominent benign browser incompatibilities. The first one is different features. Web browsers can have different development status in supporting features. In this respect, some features may not be supported by each browser. For example, CSS contains strict is only supported by Chrome, but not by Safari. The second one is the different design, a different benign design. The web browser have their own unique design for feature that are underspecified in the standard. For example, the design of the input element with a file type is different in Chrome and Firefox. However, their results are both correct. So we propose AltoG2, a framework to find and analyze rendering bugs. Let me explain the overview. First, AltoG2 make a random HTML input and open it on two different versions of the same browser. Next, it checks whether the two results are different or not. If they are, it decided that input has a potential to be a bug, and we will call this case as a candidate bug. Then, AltoG2 conduct bisect analysis to find the bug commit, which first introduces the rendering difference between the two tested browsers. After that, it uses the rendering bug oracle to filter out the benign issues from the candidate bugs. Next, it performs rendering pipeline analysis to identify which stage of the pipeline triggers the rendering bug. Finally, also used to generate a final bug report of the oracle bug. While we conducted the evaluation, we found 11 new rendering bugs in Chrome. Developers confirmed all bugs, and 6 of them were fixed. In addition, AltoG2 correctly reported the bug commit of all rendering bugs. It also correctly pinpointed the bug stage of all rendering bugs except one. This means that our tool was very effective in finding and analyzing the rendering bugs. Thank you for listening.
Very nice. Thank you very much, Suwan. I'm looking forward still to having plenty of discussion quite soon. We just have one more presentation before we open the floor up for discussion and Q&A. The last presentation is going to be algorithmic profiling for real-world complexity problems. And that's going to be given by Bokwin. So Suwan, if you could stop screen sharing. Excellent. Very good. Thank you. Take it away. Bokwin, are you able to unmute? We see your screen share, but we can't hear you or see your video.
Now,
Yes, we can hear you now. Maybe just some weird concurrency bug. Can you try to screen share again?
okay, yeah.
Awesome.
Is everything okay?
Perfect. Thank you very much. Go ahead.
Okay. See. Hello, everyone. I'm Bo Qin from China Telecom Cloud Computing Corporation. Welcome to my talk. In this talk, I will present our PSE paper, Algorithmic Profiling for Real-World Complexity Problems. This is joint work with Tengfei Tu, Ziheng Liu, Professor Tingting Yu, and Professor Linhai Song. Complexity problems are a special type of performance bugs. They are caused by algorithmic inefficiency. Here is an example from MySQL. Function XML parent takes two parameters as inputs. The first parameter, items, is an array of XML nodes. A nodes level field represents the node's XML nested level. The second parameter is an array index. The function searches the parent of the node, indicated by the second parameter. The loop iterates through items backwardly and searches for the first node, whose level is one less than the input node. The piece of code looks innocent. However, there's an outer loop not shown in the figure. The outer loop keeps calling the function using the next sibling of the previous XML node. Thus, the function has n² complexity in the number of children of a parent node. Developers may think using an implementation in n² complexity is fine, since an XML node usually does not have too many children. However, during a performance failure run, an XML node has tens of thousands of children, leading to a significant slowdown perceived by the end user. The patch is to add a new local variable in the outer loop to keep track of the current parent, and completely remove the call of function XML parent. Many complexity bugs are like this MySQL bug. They cannot be optimized away by compilers. Fixing them can gain huge performance improvement. Moreover, complexity bugs widely exist in software. As shown by our empirical study, they cause half of the user-perceived performance issues. Programmers usually rank complexity bugs as high priority in the development. For example, Mozilla developers will immediately try to fix complexity bugs degrading exponentially. Therefore, it is important to combat complexity bugs. However, fighting complexity bugs is challenging. A good technique needs to satisfy three requirements. Firstly, it must provide precise execution complexity for each piece of code. Second, for a slowdown caused by a complexity problem, the technique must accurately pinpoint where the root cause is. Third, it cannot incur a large runtime overhead because it is desired to run the technique in production runs to determine whether a complexity bug causes real performance impact and deserves to be fixed. In our paper, we designed COM-AIR that satisfies the 3 requirements and can effectively detect complexity bugs. This is the infrastructure of COM-AIR. And here are the conclusions. First, we conduct the first empirical study focused on complexity bugs, where we studied 36 real-world complexity bugs and obtained 3 implications for algorithmic profiling. Then, we implemented COM-AIR, a practical algorithmic profiler, which can work under both production run and in-house settings. It provides a novel ranking mechanism to identify root causes with fewer FPs than APROF and OProfile. More importantly, the runtime overhead under production run setting is constantly under 5%, making it practical for production run environment. For more details, please refer to our paper. Thanks a lot.
Fantastic. Thank you very much, Bo-Chin. Very interesting presentation. So at this point, we're going to switch from a presentation mode and into a completely open Q&A and discussion mode. Please feel free, again, you can write your questions in the chat. I'd also be happy to invite question askers to turn on their video and microphone if you'd like. This is a regular video call, kind of like Zoom. Anyone can turn on video and be online. I think that we already have at least one question in the chat, though, so we can start with that one. Question from Hanyang. Feel free to unmute, otherwise I'll go ahead and ask it, not a problem. I think that this is directed at the multi-language regression test selection paper. Yeah, so the question was,
yes.
Daniel, you analyzed syscalls to construct a dependency graph. The question is, if you have access to source code, why not construct a dependency graph using program analysis techniques like SciUnderstand?
Yes, so that's a valid question, and we actually considered that. There's one advantage of using file or tracing file-related syscalls, and that's that you can see all opened non-code artifacts or DLLs. And I said we have these cross-language links a lot in the code base. And also we can see what that are commonly spawned by tests will, what kind of files are opened by these subprocesses if we transitively collect all the files opened by also child processes. So that's an advantage that we could not do, or we could not implement that if we only instrumented, for example, the Java IO classes and only kept track of the open files through Java IO. So that's why we use system call tracing in this case, and also it makes the technique more transferable. So also if there is some non-artifact, non-code artifact opened by some DLL, we will also keep track of that. And that would also be missed if we only instrumented at the Java source level.
Very interesting.
Does that answer the question?
I think so. I have a follow-on, very quick.
I hope so.
How
Please.
Exactly did you capture? Oh, I see. Hanyang is coming on. Oh. How exactly did you do this instrumentation to capture system calls? Like, at what level were you interposing?
Yes.
We're in libc. Did I miss this part?
Yeah. So we used dtrace for that. And that's basically a probe-based system call tracing approach. So you essentially hook actions into precompiled probes inside the operating system kernel. And dtrace is just one alternative that works on Windows and on macOS. And then for Linux, you could go to BPF trace. I think that's very popular in recent years, for doing this kind of system call tracing. So that would be an alternative way to do that probe-based system call tracing in other operating systems.
Very good, thank you. Are there other questions from the audience?
Can I
Go ahead,
ask
Stefan.
questions?
Yes.
Yeah, I want to ask a question about performance bugs in DBMS. So you designed 75 mutation rules. I think it's manually designed by experts, right? So is there any way to automatically discover those semantic preserving rules? Like if you take a close look at how the optimization is implemented in the DBMS system, will you be able to come up with something that is automatic? That's all. Yeah.
Thanks you so much for the question. I think it's a really so the 75 mutation rules we select are from an existing query optimizer, and these rules are guaranteed to preserve query semantics because the it's by design. It's preserve the semantics. And in order to design a rule that preserves semantics, you need to check the format of the query planetary and also the schema of the database. So actually, it's a very complex. It's a very complex. So each mutation rule has very complex logic. But so indeed we can expand the mutation rules by fuzzing some existing rules, by adding some unnecessary operations that preserve the semantics, such as if you already have a group by operators, you can still add the same group by operators and add because like adding another groups, the same operators will not change the semantics of the query semantics. But if you if you want to add, so there are two alternatives. One is to have a very rigorous query optimization foundation to have the query mutation rules. The other is to expand the existing ones just by adding the duplicate operators. So in that case, you may able to check whether the DBMS can intelligently remove unnecessary operators. And in fact, there is indeed one case when we submit to the PostgreSQL developers, is that there are duplicate operators and they are recognized as missing optimizations, but they plan to not fix it because their expectation is that the developers won't write such queries. So actually a key findings, a byproduct finding of our work is that the declarative SQL fails to deliver one of its key promise, which is that when the SQL users write queries, they do not need to care about the query performance. But as shown in our bug report results, so different DBMS developers have different interpretation of missing optimizations. So I hope my very long answers quite a part of your questions.
Yes, thanks. Yes.
Thanks for the question.
Stefan, do you have a question?
Yes, I actually have a question for everybody who reported bugs to developers. So in our study, we received very mixed feedback. So those were all clearly bugs, so the software were crashing. So there's no way to argue that this is intended behavior. But what we observed was that while with scikit-learn, they mostly cared, they also didn't always care. So for example, we had one bug we reported where basically any regression model crashes if you have data larger than 32 bits. So they crash, and they crash with an error message that is in no way related to this error. And most scikit-learn models that cannot work with this data give you a very nice error message. It says, okay, please use data in this range. And then they were like, yeah, it crashes. And only later they realized, oh, this can hide all sorts of errors. And well, with Weka, they said, okay, we're in maintenance. Spark said it's a corner case. It won't happen in real data, at least we hope so. So what we're wondering is, especially if you're using fuzzing or something like that, where you might also generate unrealistic inputs, did you observe similar interactions with the developers, or were your bugs readily accepted? So some of our bugs were really accepted enthusiastically. One was fixed within 24 hours. And for others, it was really, well,
Yeah, thanks for Stephen for proposing this nice question. I think this is, I mean, almost all fuzzers have this problem. So if you submit a bug report, then the developer will think, I mean, because most of the time it's about, most of the time it's invalid input due to invalid input. So, but sometimes the input is valid, but it's so weird that nobody in real life will write such code. And in our case, because I test deep learning libraries, mainly PyTorch and TensorFlow, and from the developer side, sometimes I will feed some very weird values into some parameters. For example, negative values into an integer, which shouldn't happen. But if it crashes, like segmentation fault, then the developer think this is high priority bug, because they don't want the system to crash unexpectedly. And also, if you pass some zero-dimension tensor objects, then and on TensorFlow it sometimes crash, and developers are treat our bugs in a very welcome way, and they think, yeah, we will to fix this, and that's what I observe in my testing scenario and in my research. But sometimes it doesn't. So, but for some types of bug, it shouldn't happen. Nobody will write such kind of code, even if it's invalid, and then it will be neglected. So
nobody doesn't want to attack your code will write that. So nobody who don't wants to poison data or who wants your models to crash. And I think they sometimes ignore this actually real life usage.
That's right. Yes. Thanks for proposing the question. I don't have a sound answer to this, but I think it's interesting.
But it's interesting that you really observe the same issues. That's really what I was interested in. If others who report these kind of bugs encounter the same kind of pushback sometimes.
Yeah. So I'm curious also how maybe others ran into similar issues when using different kinds of oracles. So like in Anjiyoung's case, when we're talking about like the no crash oracle, like it's maybe or a differential oracle, it can be pretty straightforward to say like, well, it shouldn't do that. But I can imagine that particularly as we get closer to like the performance kinds of issues, or the rendering kinds of issues, the definition of what a bug is could be more subjective to the oracle too, like not just the input. And I'm curious what kinds of issues. I know that Xinyu mentioned that there were some unconfirmed bugs, or some that were found to be false positives. Like, could you describe a little bit about like what those bugs were and like what was going on and what the developer response was?
So actually, we have quite different responses from two different DBMS. So CockroachDB folks reacted more positively, the confirming most of the bugs we reported and fixing 5 of them. And the PostgreSQL developers reacted less positively. But the interesting, so which shows that different DBMS hold different like interpretations of the definition of performance bugs. But actually, there is indeed one case in PostgreSQL report that, although they do not acknowledge as our report as a performance bug, but it matches a planned fix, which at least indicates that this particular missing optimization is worth addressing. So the takeaway is that our tool is useful for detecting such performance issues, but it is ultimately the developer's decision whether to address it. So and so actually there is another bug report that even though the PostgreSQL developers do not acknowledge it, there's a follow-up question from SQL users on how to write efficient queries to circumvent these missing optimizations. So that's also indicates a case that our tool Amoeba discovered interesting performance inefficiency issues, and but it is ultimately the developer's decision whether to address it.
I have a question regarding rendering regression.
Alex, you're cutting echo. I don't know if you maybe while you're asking, or if you have an extra browser tab open. Not sure.
Is it better now without echo?
Yes, perfect.
Okay, so I will repeat the question again. So regarding the rendering regression in the browser, I have a question about the differences in the browsers. So some differences, or like there's many differences in the rendering that is not considered bugs, but browser render that differently. So how you deal with that exactly? I know like you mentioned that in the presentation, but I didn't really get how we differentiate that when it's not just a small component like a file input component, when like the whole page has, for example, different thickness of the line or something like that. It's not something small that you can isolate it.
We actually we designed a regression oracle, and we actually use 3 browsers. One is the older Chrome, and the other is the newer Chrome, and the other one is Firefox. So we compare 3 results, and let's assume that if the older and newer one generate a different result, and the older Chrome and Firefox generate the same result, we can infer that the older Chrome and Firefox might be correct because they generate the same result. So in the case of the input file, we cannot detect. So it is kind of false negative because we cannot detect kind of that bug. But our focus is to find regression bug without the first positive issue. So we focus on the first positive issue. So we discard all the first negative issues. And yeah, so if older Chrome and Firefox are the same, so your Chrome might be incorrect. So we are thinking that older Chrome was correct, but after the update, the newer Chrome introduced the bug. So we can say that there is a bug in your Chrome. So we regard that as a regression rendering bug.
Just a follow-up question. So simply, if the older Firefox, for example, and the older Chrome have different rendering, this will not be considered for any future testing. So you just use
that's correct. Yeah.
when the older versions have the same exact rendering.
Yeah. So yeah, that's correct.
Thank you.
Thanks. Maybe a follow-up. There's a question in the chat from Daniel, also for Suwon, of how R2Z2 guides the input generation to find specifically error-prone HTML, CSS inputs.
Thank you for your question, and I think it is a good question. Actually, we just leverage the Domotor fudger, which is built by Google, we use it, and we do not guide the input generation. But I think if there's a input guidance to maybe better finding regression bug, I think it might be great. Yeah, but we do not use the input guidance.
So is it just randomly generated HTML, CSS code, and then you hope to find something in there?
That's correct. Because our, I think our paper's contribution is finding the regression, actually detecting the rendering bug, false positive, and automate the bisect analysis and pipeline stage analysis. So that's all. That's our contribution, and yeah, but input generation might be helpful.
I have a question for you. So you mentioned in the paper that there is one bug stage which cannot be pinpointed by your technique. Can you discuss that specific bug? Why?
Because we got the developers, but when we asked the developers the bug stage of the bug, but they said it is. They said they cannot determine which stage triggers the bug, so we just leave it as a undecided issue.
Oh, I see. So you don't have the oracle from the developer, so you don't know whether your pinpointing is correct or not. I see.
That's correct. Yeah, and also, that's correct. Yeah.
I have a question for Daniel. I'm curious if it's a problem or might be running into at some point for tracking coverage of files on different machines. Like if the company might have a multi-language project that also resides in multiple processes, and maybe there are some like end-to-end test suites that involve like spinning up some Docker containers and running requests against that also. Is that something that is like on the horizon to support in the future? I've never seen a system that actually supports that. It would be very cool.
Yes, so I think that is a problem. So for example, if you have some kind of Docker volume where some of the files are located, and then inside the Docker container, some file opens are issued, you probably won't be able to trace that unless you get the system call tracing somehow mounted inside the Docker container, which is technically possible, but we haven't experimented with that yet. But what we are currently doing, because we do have an imprecision problem in some language environments, for example, anything that compiles to binary essentially is a problem, because there we won't see any accesses to class files as we do in the JVM environment. In this case, we need some kind of instrumentation, and for example, dynamic binary instrumentation is also a language agnostic way to achieve that.
Cool. We ran into similar kinds of issues. We did some coverage stuff with Deflaker and trying to identify which tests execute which code when you have servers. It's not an easy time. I don't envy whoever has to do that.
So I think end-to-end tests are particularly tricky. We're also experimenting with them, and it's difficult.
It's interesting because they also might be like the most expensive ones to run. So where you might get the most like
correctly.
You're like, well, this test takes 5 minutes to run, so not running it is even better than not running the one that takes 100 milliseconds. But all the
yeah, and I can even say that we specifically also are interested in manual tests, which are by nature somehow system tests or end-to-end tests, and those have even more effort, and still people do not really optimize them yet. There's very few research on manual tests, and
Yeah.
I think that would be particularly interesting to extend it in that way.
Interesting and important and difficult research, and I hope that somebody is doing it. Well, I would like to thank all of the speakers once again, and all of the audience members and participants who came, who stayed, who asked questions, who engaged. I had a lot of fun. I think that this is certainly a nice format to compromise if we can't see each other in person. Hope to see and meet folks in Pittsburgh or another day.